Hello everyone, myself Nikhil Gurnani,
Myself Karthik Desai.
and we are here for presenting you a podcast on the topic pressure and velocity distribution of a rotating sphere in the fluid. Also calculate the torque acting on the fluid by the sphere. And our second topic is
Our second topic is a dimensional analysis of Navier-Stokes equation in spherical coordinate system.
so here, starting with the reading the question as there on the screen, it was case 4 under the Navier-Stokes equation analysis. The case said a solid sphere of radius r is rotating slowly at a constant angular velocity omega in a large body of quiescent fluid as shown in figure. So the figure shows that a solid sphere it is rotating in the large water body as mounted with a stick or like stick on mounted on its top, so that the figure is like such a lollipop like structure. So the sphere is rotating in the fluid body, and the pressure and velocity distribution in the fluid we have to study. Also the torque exerted by the sphere on the surface of the fluid we have to study. So the question says that develop expression for the pressure and velocity distribution in the fluid and for the torque Tz required to maintain the motion. It is assumed that the sphere rotates sufficiently slow with a constant density and viscosity system. Also neglect the effect of gravitational forces. So now coming to the given statement in the question, firstly we have given a solid sphere of radius r which is submerged in an infinite or quiescent. Quiescent means stationary fluid and rotates at a constant angular velocity omega. Now here comes our assumptions that the fluid is constant density, the fluid is of constant viscosity. Also, we have to neglect the effect of gravitational forces. Now our goal is to derive the velocity distribution, which is mainly three types of velocity: Vr, V theta, and V phi. Uh, in those three types of velocity, in this case, 2 may be 0 because the system is symmetric, system is solid inside the dimension r. So we are like the particle is solid inside the sphere, so we are mainly we can assume to be 0. Let's see further in the question what's happening. And the pressure distribution also we have to study, and the torque required to maintain the rotation. Okay.
Next, step-by-step analysis of our problem. Number one, assumptions and simplifications. First, we will see assumptions and simplification. Number one, we will assume creeping flow. It means laminar flow. It has low Reynolds number. We will see inertial forces are negligible compared to viscous forces. Number second, we will see axis symmetry, which means no dependence on phi. We will see dou by dou phi is equal to 0. Number 3, we will see radial, no radial or polar flow. Vr is equal to 0 or V theta is equal to 0. Number 4, steady state. There is no change with respect to time. It means dou by dt is equal to 0. Number second, we will see governing equation, which is spherical coordinates. The Navier-Stokes equation simplify to equation number one continuity equation, which means del dot v is equal to 0. Number second, momentum equation, which has three components. We will see one by one. First is r component, second one is theta component, and third one is phi component, which is simplified as Navier-Stokes equation. Now we will see part number 3 for solving the case number 4 of spherical coordinates.
Now third step of the analysis is we have to solving the phi component of the velocity. Now let us assume the phi component is some function of r and multiplied by sine theta. So as instructed in the class, the equation is very complex to solve for the phi component. So we have been instructed to assume something like in mathematics. What is if something is very complex, like solution of very equation is very complex, so we can assume any function which will be the solution of our differential equation. Then proceed further. So if our assumption is right, then the equation will be proceed accordingly equal to our assumption. So our general solution which we'll be assuming is v phi equal to fr some function of r into sine theta. So the general solution of this assumption came out to be fr equal to c1 multiplied by r plus c2 divided by r square. Okay, then this will be mainly general of equation. So we have developed mainly equation part. Now solving the equation, we need some boundary condition. Like there are several boundary conditions in case of sphere, in case of cylinder, in case of our Cartesian coordinates. So the mainly boundary condition used here is first is no slip condition. At r equal to capital R, we have v phi equal to r omega into sine theta. So at let's say 90 degrees, sin theta equal to 1, and our fr becomes rho into omega. Our second boundary condition is far field quiescent condition. Quiescent condition means if we are rotating our sphere at very constant, very small velocity omega, then disturbance by this sphere is due to very small distance. Like the disturbance cannot be go very far. Like if our rotating any very small sphere, like 2 or 3 centimeter diameter sphere in the very large swimming pool, so that effect is very small and it will be only at very less space. So the this assumption is says us that the velocity impact on, like say we have rotating our sphere at one corner of the swimming pool, so the effect of this rotating sphere at the another corner of the swimming pool is will be negligible. So v phi is 0 at r tending to infinity. So this boundary condition makes us our constant c1 equal to 0. Now, by using these two boundary condition, we can get our final velocity profile, which we'll be discussing in further, and also this indicates our pressure distribution, mainly differentiating in r and theta direction. Using these two boundary condition, we can get our pressure distribution also. And key insight of this process is pressure decreases near the equator due to centrifugal effects. Like our sphere contains of an equator, and our longitudes and latitudes mainly are polar coordinates. So where the sphere is mounted on the top, their pressure is very high, and pressure decreases near the equator due to centrifugal effects. Now, calculation of torque. Firstly, by using of Newton's law of viscosity, we'll calculate the shear stress distribution along the sphere, and by the we have getting shear stress, we could double integrate it with the d theta and d phi. We could get our torque. All that further calculation we'll see in the video.
Now we will see key takeaways. Number one, low Reynolds number flow dominated by viscosity reversible streamlines. We will see application of this problem. Number one, rheometry, measure fluid viscosity via torque. Number two, microswimmers. Bacteria, flagella operate in this regime. Now we will see limitation fails at high omega, which means high turbulence or non-Newtonian fluids. We will see visualization of this problem. Fluid near the equator moves fastest, creating a uh, creating a toroidal vortex if omega is high enough. Number two, pressure drop at theta is equal to pi by 2 can cause cavitation in extreme cases. Further exploration. Number 1, Stokes drag versus rotational drag. Number 2, unsteady effect. How V phi evolve if omega suddenly changes. This case this case shows Stokes flow, a cornerstone of microfluidics, biochemicals, and lubrication theory. Number 5, we will see torque calculation, in which we see number 1, shear stress on sphere calculation, and number 2, torque calculation, which is integrate over sphere surface.
Now moving on to the physical interpretation of the problem, as we have derived the velocity profile, as we have derived the torque proportionality, as we have derived the centrifugity of the problem, we can show that the velocity decay and it follows the inverse square law. That means the velocity is proportional to 1 by r square, which means as we are increasing the radius, the velocity decreases by the square of radius, you know. And it also shows that the torque proportionality shows that torque is proportional to our viscosity, our angular velocity omega, and cube of our radius. So as we move further, as we move away from the sphere, torque also increases. And as we move, torque was increases means torque is we need higher torque to rotate our sphere. Like large radius comprises to larger torque for rotating the sphere. And angular velocity, like if we need very high angular velocity for rotating sphere, in our case, we need higher torque. It will be obvious that angular velocity will be high, so torque will be needed more. Also viscosity. The viscosity is very obvious thing in the torque calculation. Like if the fluid is very viscous, like we'll be rotating, in this case we'll be rotating in mainly water, so the rotating will be easy. And if the fluid is our honey or any oil or any fluid which will be higher density than water, then torque will be needed much more. So also, this torque technique is used in viscometers to measure the viscosity. Like this is our practical usage of this problem. Now, centrifugal pressure means the negative pressure at the equator. Explain vortex formation in stir tank. Like in stir tank, our impeller is rotating. So this kind of scenario is similar to our problem. Our sphere is rotating in the large fluid, and in the stir tank reactor, we have impeller rotating in the fluid. So at the equator, like at the point of what we say at the point of distance r from our origin, there can be vortex formation, which will be corner cases of our problem. And this we are assuming laminar flow, and this vortex formation cannot be there in laminar flow. So this kind of things came under the unsteady state of kind of assumption. And for ensuring non-vortex formation and only steady state, then we should have surprisingly very small omega and non-viscous kind of fluid, and that kind of thing we have to ensure. So now we'll be discussing the solution of our problem case, which will be we have to calculate the velocity profile of the fluid present outside the sphere, the pressure distribution, and the torque required to rotate the sphere. So our first step will be finding out the velocities. So in the sphere we have three types of velocity, which will be Vr, V theta, and V phi, along with pressure. So out of these three velocities, Vr equal to 0, V theta equal to 0, because at point of r we are having solid material, so fluid is not there, so that's why Vr is 0. And all in the theta direction the shape is symmetrical, that's why V theta is 0. Only we will having V phi as our velocity, and V phi will be depending on r and theta. V phi equal to V of r and theta. As we'll move further as distance by r, the V phi velocity will be different, and as we move in direction theta, our velocity will be different. But as we move in phi direction means rotating the sphere in this way. Like this is our sphere and we're rotating it in this way. So this will be, the velocity will not be varying because it will be symmetric in phi direction. Now talking about our boundary conditions, we will be having three boundary conditions. Our first boundary condition is at r equal to capital R, we have Vr equal to 0, V theta equal to 0, and V phi equal to r omega sin theta. And our second boundary condition is at r tending to infinite, means that as I explained before, if our sphere is rotating at one corner of swimming pool, So at r tending to infinite means not exactly infinite. It means that the other corner of swimming pool. So the length is very much larger compared to r. Then our vr tending to 0, our v theta tending to 0, and our v phi also tending to 0, because it has negligible effect at very large distance. Now our third boundary condition is, as r tending to infinity, our p tends to p naught. That means our pressure will be p naught. Now coming forward, we will having three equations of Navier-Stokes for spherical coordinate. One is like Navier-Stokes equation for spherical coordinates. So we will be having three equations for Navier-Stokes equation. First for r equation of motion, second for theta equation of motion, third is for our phi equation of motion. So as in our question, our Vr is 0, our V theta is 0. So we'll not consider our Navier-Stokes equation for r and theta direction, but I will write it once, but then we'll neglect it. So r equation gives rho del Vr by del t plus Vr del Vr by del r plus V theta by r del Vr by del theta plus V phi upon r sin theta del Vr by del phi minus V theta square minus V phi square upon r equals to minus del p by del r and plus mu 1 by r square del square by del r square of r square Vr plus 1 by r square sin theta del by del theta of sin theta del Vr by del theta plus 1 by r square sin square theta of del square Vr by del phi square plus rho into gr. This will be our Navier-Stokes equation for r direction.